Very good. Oh, man. Seems criminal that we're inside right now.
Okay, I think everyone is in. Couple of administrative items today before we delve into first order circuits. So I think we're almost ready to start the labs. So my plan is to have the first lab occur next Monday, which will be April 26th. And we're actually gonna try to at least start it during the lecture time. So the TAs have done a really nice job in adapting the previous labs into, the new circuit kits that you will be using. So and I'll put out an announcement on Blackboard, but probably at about 3:30 next Monday, we will switch from my blathering onto the TA's instructions on how to use your breadboards and your DAC cards. And so for next Monday, just have your circuit kit with you during the lecture. So, and then we will use, my plan is, I think we have 5 more Mondays, including today. So we will have the next 4 Mondays after today will be split into lecture/lab. And so, which is the way the course is always run.
Just to add to that, before, like, I think we will try to send out the lab manual to you guys before the next lecture. Just to prepare, please, from it. Like, even though you don't know what the component in the circuit kit, just take a look and familiarize yourself with like all the component, and also install the software on your computer, so we can send like a lot of time like in waiting for you guys to install the software before we can get started. That's all.
Very good suggestion, Sam. Definitely you want to have the the acquisition software installed. That's definitely a good idea, so that no one has to be doing that during the actual first lab. What else did I want to say?
I have a question.
Go ahead.
To return the circuit kit, do we like return it in person, or do we keep the boxes that it came in so we can return it? Or
yeah, it's going to be a whole other adventure is getting these things returned. I mean, that'll happen during the summer. And it'll, if you're in, so I actually have to talk to Professor Parr about that, because Professor Bixson maybe, they do have to be returned, but there may be some flexibility into how they are to be returned. I mean, one option for those of you that are outside of the New York City area, they'll have to be mailed. And for those of you in the New York City area, maybe there can be some way of coordinating bringing it back onto campus. I have to talk with the other faculty that teach circuits courses in the program and figure out when the next cohort will need them. They may not be needed until next year's 205, but yeah, they do have to be returned over the summer. So again, for those of you that came in late, we're going to be using not this Monday. This Monday is, well, today's lecture is going to be kind of grueling. But the next month, the next 3 or 4 Mondays will be split between me lecturing and the TAs leading the labs with the circuit kits. There'll be 3 or 4 modules that you will carry out, and we are gonna try to use some of the lecture time so that you guys can do the lab with some supervision. So that was the first announcement. The labs are going to start next Monday, and I'll probably stop teaching at about 3:30, maybe even earlier, maybe even at 3:15, just to give you guys an hour and give the TAs an hour and a half to kind of give you an overview on how to use the kits, how to make basic measurements for voltage and current, how to decode the value of a resistor from the bands of color that are wound around the resistor. Yeah, so that will begin next Monday. Homework 4 is posted. It is due 1 week from today. It is not a long homework. And homework 5 will be released shortly after homework 4 is due. I'm in the process of getting through your midterms. I hope to have grades for you guys this week. And lastly, we have 9 lectures left, as far as I can tell. And we have to get through the rest of lecture 7, then lectures 8, 9, and 10. So I went through and tried to divide up, how many days I think we need to cover each of those lectures. So lecture 7 and 8 are the longest. So I'm going to say that we're going to spend 2 more days on lecture 7. So this week we will finish lecture 7. Then the next 3 lectures will be towards lecture 8, which is like the climax of the course, the apex, the pinnacle. And then lectures 9 and 10 are like the come down, and we're going to devote 2 lectures to 2 sessions, whatever you call this, 2 of these lectures into lecture 9 slide deck and 2 more to lecture 10. And that will allow us to get through everything. It's a little bit optimistic. And what I'm probably going to do is, beginning today, is I will not work through every example or every practice problem in the slides. Simply, there's just not enough time in this course. And so some of the material I will encourage you to view on your own time, and I may even try to record some supplementary lectures that cover those problems that we didn't get to in the live lecture. All right. Is there any questions before I begin presenting lecture 7 content? All right. I believe this is where we left off. I hope I'm not wrong. All right, so we covered RC circuits, which had a resistor in series with a capacitor. So today we're going to actually cover circuits that combine resistors with inductors. So here is our kind of standard picture for an RL circuit. And so the way that these are depicted, it looks like the resistor and the inductor are in parallel, right? Because the VR here, well, if you flip the polarity of VL, they'll be equal to each other. But actually, these 2 are in series. You can actually, the way they're defined here, this is actually a funny picture because they're in series and in parallel in a way, right? Because they share current and voltage. And the key difference between RC and RL circuits is that in any RC circuit, you will be solving for the capacitor voltage. In an RL circuit, you will be solving for the inductor current. So whenever you see a capacitor, think voltage. Whenever you see an inductor, think current. Right, so that's the first point, that we are going to be interested in finding an equation for I of t, which is the current through both the resistor and the inductor, but we're specifically interested in the inductor Why? Because it obeys continuity. So in other words, we saw that an inductor will oppose an abrupt change in the current through it. And so we can assume that across any time boundary, that variable will be continuous, and we will be able to use its value as an initial condition. Okay, and so we assume that at time equals 0, we know what the initial current is, or we will solve the circuit to determine its value. So I naught is the value of the current flowing through the inductor at time 0, right? So in this picture, the current is flowing clockwise. And we know from previous lectures that the current stored in the inductor's magnetic field is equal to 1/2 Li squared. So this is the amount of energy that's being stored in the inductor at time 0. So let's now apply KVL around this loop. Very straightforward. We have if you go clockwise, you have 2 voltage drops, VR plus VL, and those two have to sum up to be 0. And we have expressions for both VL and VR in terms of I. Right? So VR from Ohm's law is just equal to I times R, and VL is equal to L times the derivative of I. So let's plug these into this equation. And this slide gets a little bit crammed, I apologize. But you end up with a first order differential equation, which you have no doubtedly seen before. And basically, if you so this is the result of substituting these voltages into the KVL equation. And then to go from here to here, we just divided everything by L. And then to go from here to here, it's just, you just move over the R over L times I to the right side and divide through by I, multiply through by dt, and you get to this integral equation. So you basically, you rearrange and you integrate both sides. And what was an integral across time on the left side now has become an integral of current. And we know that the integral of 1 over I is the ln of I, right? And the integral of a constant is just a linear function. So now if you plug into evaluate the integration limits, you get that the natural log of I of t minus the natural log of the initial current is given by negative RT over L, right? And so this function here, as time increases, will become more and more negative. So the natural log basically becomes more and more negative as time goes by. In other words, the inductor current will generally be decreasing with time in this circuit, right? And so we know that the difference of logs is equal to the log of a quotient. And now we can finally exponentiate both sides and arrive at a very similar looking equation as what we saw for the RC circuit. Okay, the only difference between this equation here and the RC circuit equation is that now instead of a voltage, we're measuring a current. And instead of the time constant being R times C, the time constant here is given by L over R. Okay, so I think we'll see it on the next page. So the time constant of an RL circuit, tau, is given by L divided by R. And then the current through the inductor is again given by an exponential decay from some starting value down to 0 eventually. And at every tau units of time, that value decreases to 37% of its previous value. So it's just like what we saw for the capacitor voltage, but now it's expressed as the inductor current. So when you're faced with an RL circuit, you can either just memorize and apply this formula, or you can always go back and try to derive it. but this will be the canonical equation here that you basically have to know. Okay, and so if you know I of t in this picture here, if you know I of t here, then you can just multiply it by the resistance to get VR of t. So VR of t is the resistor voltage, and it's just equal to this current multiplied by R. And you can do the same thing as we did before by power is the product of voltage and current, right? So the power, dissipated in the resistor is the product of the current, which is common to the resistor and the inductor, times the voltage. So you basically take this equation, square it, and multiply it by R. Okay, and so to the power, this is an instantaneous equation. I think that confuses a lot of people. Power is still an instantaneous quantity. So it's still a function of time. To get the energy, we have to integrate across time. And so if you integrate this function, it's a little bit of manipulation, but it's not hard. I just have to know how to integrate it an exponential. And if you evaluate it at time t, what you see is that the power, the energy rather, that is absorbed by the resistor is equal to 1/2 Li naught squared times 1 minus a decaying exponential. So let's take the extrema here. Let's take t is equal to 0. If t is equal to 0, then what happens to this quantity WR here? What's the energy stored in the resistor at time equals 0?
Just half the Li squared.
So we have 1/2 Li naught squared, and we also have on the chat, we have I naught. So I believe that both of those are wrong, but I just want to, sometimes I'm wrong, but I believe that. So what happens to the term in parentheses here as at t is equal to 0? There we go. That's the correct. I believe that's, yes, those are both correct. I believe that the answer is 0. And the reason is, well, mathematically, it's because this term here evaluates to 1. And so we have 1 minus 1. So anything multiplied by 0 is 0. And so WR at time 0 is equal to 0. And so the reason that it's 0 from like a circuit's point of view is that right at time 0, there has not yet been any time for the current through the inductor to be transferred as energy to the resistor. So it will start to accumulate after time 0. And so let's take the other extreme now. Let's take time equals to infinity. What happens to this term? Open up the chat. So what happens to the energy absorbed by the resistor at time equals to infinity? Yes, there you go, Christian. It is 1/2 Li squared, because at time equals to, someone's already had enough. The reason is 1/2 Li squared is because all of the energy that was stored in the inductor has now been absorbed by the resistor, right? So basically the inductor has become a short circuit and the current is just flowing around that circuit. Okay, so as time goes to infinity, all of the initial energy that's stored in the inductor is dissipated in the resistor. All right, the important stuff, the steps to working with a source-free RL circuit. So source-free just means that after at time equals to 0 and subsequently at any time greater than or equal to 0, there are no batteries or current sources connected to the circuit with the inductor in it. So the first step is to get the initial current I0. To get that initial current, you either have to solve a circuit or it's given to you. Step 2 is to get the time constant. So this is basically the amount of resistance that the inductor sees when all the sources are turned off. So it's like the equivalent resistance as viewed from the inductor. And then step 3 is just to combine steps 1 and 2 and put them into the nominal equation, which is that the inductor current at any point t is equal to I0 times e to the minus t over tau. And remember that tau is equal to L over R, whereas hold on. Right, so whereas before tau is equal to R times C, now tau is equal to L over R. And we'll do a couple of examples. All right, the last note here is that once we have an equation for the inductor current, we can use it to solve for the other elements in the circuit, such as the voltage of the inductor or the resistor voltage or current. Okay, let's do one of these examples. We have the following circuit. So it's a circuit with a dependent voltage source whose value is 3I. So the nice thing is that we are told what the initial condition is. We're told that at time 0, there's 10 amps flowing down here. And we are asked to find I of t and Ix of t. So we need a time. We already have the initial condition. So all we need is a time constant. So how do we evaluate the amount of resistance that is seen by this inductor? No guesses? Okay. Well, let's okay. So first of all, there's 2 ways this can be solved, probably more than 2 ways. The first way is to get the equivalent resistance from the inductor, from where the inductor is. The second way is to actually, from first principles, apply KVL. But I like the first way here. I like to try to find a solution to REQ. Okay, so the way to do that is to basically put a test voltage in place of the inductor and measure how much current flows out of that test voltage. The reason we cannot just measure resistance directly is because we have a dependent source. And whenever you have a dependent source and you want to measure the Thevenin resistance, you need to apply a test source, either a test current or a test voltage. So let's put in a test voltage here. So this is in place of the inductor here. And then, yeah, and this becomes basically a 2-mesh circuit with 2 voltage, with a independent voltage source and a dependent voltage source. And so we have the mesh, there's 2 mesh current equations here. So who can help me come up with the KVL equation for mesh number 1?
One
Yep.
plus 2I1 minus I2 equals 0.
Excellent. That is exactly right. Sorry, my Zoom windows here are blocking the answer. Yeah, so it's 2 times I1 minus I2. That's the voltage drop from here to here. Notice that here, the mesh arrows have been drawn counterclockwise. Right, so we're going, and I guess I don't know what the reason is, but it doesn't really matter which way you draw them, as long as you obey Ohm's law. When you write your KVL equations. So going counterclockwise, we have a drop of 1 volt, and we have a drop of 2 ohms times I1 minus I2. And the second KVL equation is, we have 4I2 plus 2 times I2 minus I1 minus 3I is equal to 0. So there's a little subtlety here. It's that, let me go back actually. Notice that I is defined as the current that's flowing down through the inductor, which has now been replaced by a battery. So this I here, because it gets confusing with there's an I naught, I1, I2, and an I. So the I here corresponds to the same I as I1. And therefore you can replace in the second KVL equation, this is written as 3I1 because 3I is equal to 3 times I1. Because it's not drawn here, it's the current flowing down the battery, which is equivalent to mesh current I. So we have our 2 KVL equations, and we have our 2 variables, I1 and I2. So we can use substitution or whatever technique you like, and you obtain an equation for I1. And I1 here ends up being minus 3 amps. So in other words, the current is flowing clockwise. So the I naught is actually positive 3, right? Because I naught has the opposite direction as I1. And so if I naught is equal to 3, and we applied a voltage, so we applied a voltage of 1 volt and got a current of 3 amps out. So what that means is that our Thevenin resistance is equal to 1 volt divided by 3 amps, which is equal to 1/3 of an ohm. Okay, so that's the hardest part of solving this problem, is just getting the REQ. And again, what we did, just to go through the steps, is we replaced the inductor with a test voltage. We wrote out our 2 mesh current equations, and we solved for the current that flows into the circuit when you apply a test voltage of 1 volt. And so the REQ is equal to 1 volt divided by 3 amp, which is 1/3 of an amp. And so now we get our time constant, which is given by the inductance, which was given to us at half a Henry, divided by 1/3 of an ohm. And so our time constant is 1.5 seconds. That's a very long time constant. And so our equation becomes I of t is equal to I naught times e to the minus t over tau, where I naught is 10, that was given to us. And our time constant, t over tau, can be written as t times 2/3. Okay, so I'm going to pause here for a second just to let anyone jump in with questions. Okay. So basically the approach is to use the canonical form, solve for I naught, which in this case was done for us, and solve for tau, which we did. I'm going to skip the second method. I'm going to let you work on it on your own, look at it on your own time. Basically, it's just writing out the KVL equations directly to the circuit. I don't think that it's critical, so and because we are starting to run short on time, I'm gonna go right past it because it gets us to the same answer anyways. All right. Our first practice problem in the RL section. Okay, so we have kind of a similar looking circuit. We have again an inductor. And we again have a dependent voltage source over here. We are told that the initial current through our inductor is 5 amps. And we are asked to find I and Vx. So I is the current through the inductor at any point in time after 0. And Vx is the voltage across the 3 ohm resistor. So as before, we need to find how much resistance this inductor sees. So let's again apply the same. Oh, what happened to this? Is okay. Let me just maybe I'll do it in slideshow. This is one of those ones that I would have done on the board. But I'm going to just annotate it. I don't think it's going to be difficult. So we're going to put actually we want so we're going to put plus minus, and this is now 1 volt. Okay, so we have a 1 volt battery over here in place of the inductor. So did my best here to draw a battery, but it didn't really work out. But hopefully it's clear enough for you to be able to follow. So we again put a 1 volt source in place of the inductor. And what we're going to be solving for is how much current flows into the circuit. So this is going to be our I naught, right? So if 1 volt, let's say they produce I naught is equal to 1, then our equivalent impedance, which is REQ, would be 1 ohm. Okay. So let's actually go ahead now and work through this problem. So we're going to have 2 meshes here. Let me just see which way I had it. Just gonna try to figure out which way I drew the oops. So my mesh current equations here assume, again, the counterclockwise mesh current arrows. Okay, so again, this term here is the drop from here to here. And then we have a voltage rise of 2Vx, right? So we indicate a voltage rise with a negative sign. This term here is the 1 ohm times I1 minus I2. And this term here is just Ohm's law, 3 ohms times I1. So that all has to equal to 0. We also know that this Vx is equal to minus 3I1. Why is it minus? Because the current arrow is hitting the negative pole of this voltage drop. Okay, so now we can substitute this equation into this one, right? And we get the following equation. I2 is equal to 10I1 plus 1. So that's one of our 2 equations. The second equation we're going to get by applying KVL to the second mesh. So who can help me with the, who can help me with the KVL for the second mesh here?
Maybe 5I2 plus I2 minus I1 plus 2IX or 2VX.
Yeah, exactly. Well done. Oh, it just sucks. Hold on. Let's see if I can recover my, oh yeah, I recovered it. Okay, I think. there we go. Yeah, so exactly like you said. So I2 minus I1 is the voltage drop across the 1 ohm plus 2Vx, because this is a voltage drop when we're going counterclockwise, plus 5I2. And when you substitute our expression for Vx and evaluate, you get 7I1 is equal to 6I2. And then you can substitute that into the first. So we can substitute this result into the first mesh equation, and you get I1 is equal to -6/53. Which means, so we applied 1 volt and we got -6/53 amps flowing counterclockwise. So we actually have a current of +6/53 flowing clockwise, which means that our RTH is equal to 53/6 ohms, right? So again, our answer is negative for a counterclockwise arrow, which means that I naught, which is the thing that we're solving for, is +6/53. So 1 over +6/53 is 53/6, which makes our time constant, which is given by L divided by R. So 1/6 divided by 53/6 is just 1/53. And finally, so our answer is, I'll just try to, yeah, so it's 5 times e to the minus 53t. So remember that the equation, oops, let me try to, so we have I of t is equal to I naught times exponent -t/tau, right? And so our tau here is equal to 1/53, and our I naught here was given to us by 5. Okay, and see if I can find a way to get back my cursor. All right. Let's see. Yes. Looks like it helps to have the sorry. Yeah, my grant report. Thank you, Chrome. Yeah, that's okay. I just want you off my screen. Okay, so our let me clear all the annotation. And remember that we were also asked to develop an expression for V of X. So how do I relate I to V of X? How do I go from I to V of X? What's the current? Oh, we actually have an answer. It's good. Ohm's law, right? So, so what would be the Ohm's law expression for V of X? (3i), almost. I think it's -3i. Right. Yes, thank you. Right, so V of X is just equal to -3i. So it's just this multiplied by -3. So -15 times e to the power of -53t. All right, so here are the answers. And let me just take a look here. I'm gonna stop sharing for just a second. I just want to see how we're doing for time and whether I have yeah, so what I'm gonna do is, let me see. I think I will skip, I'll do this one. And then I'll skip number 3 because the solution to number 3 is in the slides anyways. Okay, So let's. Okay, so the difference between these questions that are coming up and the previous questions is that here the initial conditions are not given to us. In other words, we have to solve the circuit before time zero to get the initial condition, and then we have to solve it after time zero to get I of t. Right, so in this case, I naught we have to solve for. So this understanding what the symbol means is critical for you guys. So this means that this switch is in the closed position. So this is connected right up until time zero. And at time zero, the switch goes from the closed position to the open. So let's solve for I of t when this switch is closed. In other words, before time equals zero. So let's pretend that this switch is closed. And let's figure out what is the value of I of t when the switch is closed and right before that switch flips. So what I'll say is that this inductor at time is equal. So normally we use the notation time equals 0 minus. So that just basically means that time is equal to just a smidgen of time before zero. So right before that switch flips. So what will be the state of this inductor at time equals 0 minus? Short circuit, excellent. Short wire, I'll take it. I know that that's what you meant. There goes my cursor again. See if I can get it back without. All right. So right before time zero, this is a short circuit. So my question to you is, if this is a short circuit, how much current will that short circuit be drawing? The current going through the it is the current going through the 4 ohms. So any idea how much current is going? So the reason is that the current that comes out of the battery will have to go through the 2 ohms. Actually, no, you know what? I don't think that's true. So it does have to, what I just said is right, but I think the circuit, let's draw it. I actually don't remember this, so I have to draw it out. So let's draw the battery. I actually think this is going to be a current divider. This is 2, 12, 4, and the 16 is going to be gone, right? We're just going to, right? We're going to ignore this because it's in parallel with a short. And so this is 4. And the question is, and this is 40. So what is the equivalent resistance of this circuit?
Five.
5, excellent. And so it's just the 2, right, plus 12 in parallel with 4. And 12 in parallel with 4 is 3, so 2 plus 3 is equal to 5. So how much current is flowing in here? It's 8 amps. And so 8 amps is also flowing in here. And so how much of it will take this path? Well, we have a... Yeah, so the reason we are ignoring the 16 ohm resistor is because it is in parallel with a short circuit. So this inductor before time 0, before that switch flips, that inductor is a short circuit because it's effectively in DC conditions. Yes, Omar, 6 amps, excellent. There is 6 amps flowing down here, right? This is 3/4 of the resistance is here, so 3/4 of the current will flow here. So 3/4 of 8 is 6. So the initial condition for the current flowing down here is 6 amps. All right. So let me clear that. Okay, so these are the steps that I just did. So the equivalent resistance was 5, the total current was 8. And by current division, we got an initial value of 6 amps, right? Okay. So now that was step 1. This was the expression for I naught, which was step 1. So now we need RTH. And this time computing RTH is easier because there's no dependent source, right? So to get RTH, we have to look after time 0 and figure out how much resistance this inductor sees, right? So this inductor after time 0 does not see what's over here because this is now open. This is now an open circuit, so it's disconnected from the circuit. And so this inductor sees this 16 ohms, this 4 ohms, and this 12 ohms. Yeah, can I explain how I got I naught? Yeah, I can. So let me so basically the picture, try to do a better job of drawing the picture. This is our battery. This is I naught here. So this is the current that we're solving for. Okay, and this is 2, 12, and 4. And we figured out the key insight is that this is equal to 8 amps. We figured that out. So this is just current division at this node, right? So 3/4, so I naught, because of current division, is equal to 8 times 12 over 12 plus 4. So 3/4 of 8 is 6 amps. So that's how we got the I naught. All right. I can, come on, cursor. How do we get the 12 on top? Because of current division, right? Current division is if you have 2 resistors in parallel, the amount of current that flows through one of those resistors is proportional to the, like if you have this picture. Right? If you have I coming in here. Hopefully and I see there's a chat. Hopefully that's that's just you saying that you got it. Let me check. I thought it would be 2. No, that would be no, because the current is entering here, right? And it has a choice of going down to 12. Because the 8 amps that comes out of the battery all has to flow through the 2 ohms. So the 8 amps, so the battery here is in series with the 2 ohm resistor. And so, oh, you get it, nice. The way the Zoom works, I don't see what the latest chat is. I just see that there's a chat. So I don't know if the chat is saying, oh yeah, Eureka, or if it's telling me that I suck. Okay, RTH. Right, so let's draw our picture for this, for RTH. So we're going to draw our our inductor rather, just as a pair of terminals. And what do we see? We see the 16 here. We see the 4 here. And we see the 12 here. Right. So we have, so what is the equivalent resistance as viewed by this inductor in, corresponding to the picture that I've scratched out there? So which resistors are in series and which are in parallel?
So the 4 and the 12 are in series and they're in
Yep.
parallel with the 16.
Exactly.
And
Right.
the RTH would be 8.
Yeah, exactly. 12 plus. So I don't know how to say your name, Mahigul. I'm gonna guess. I'm sorry if I butchered that. Your suggestion would have been right if we are looking from the other side of the circuit, right? But we're looking from the side of the inductor, and so it matters where you're looking from, unfortunately, with circuits. And so it's actually 16 in parallel with 4 plus 12. But it's, I totally see where you were going with that. So RTH is 8, which means that our time constant is 2/8 because our inductor has a value of 2. And so our time constant is 1/4 of a second, which means that I of t is equal to 6 times e to the power of -4t. Okay. Is there any questions on that example? All right. We're going to do this one as well, and then we're going to skip the next one. So as always, the first thing we need to do is get our initial condition. So let's draw this circuit before time 0. All right, so I'm going to actually draw it, or I'm going to draw on top of it. We're going to close this switch. And remember that this is now a short circuit. Right. So looking at that, so if I short circuit this, which of these resistors can be ignored?
5.
The 5. That's right. Because if the current gets down to 12 ohm, basically the 5 is in parallel with the 2, right? I mean, that their top node and their bottom node are all the same. So we can Oh, oops, I didn't want to do that. So we can basically, we can ignore this. I don't know how to just pretend it doesn't exist, right? So there's 5 amps going in here, right? Going here. And so how much of the 5 amps makes its way down this branch? Any idea? How do I, so if there's 5 amps flowing in here, there's the answer. It's current division, right? So it's 5 times 8 divided by, well, 3. Yes, so the answer is 2 actually, right? 3 goes here, right? So it's 40% of this 5 amps flows down the middle branch, and 60% flows down the rightmost branch. Again, because of current division. All right. So hopefully everyone sees how we got our initial condition of, and let me just make clear that this means that I naught is equal to 2 amps, right? And we also know that IT is equal to I naught and the tau is equal to L over R. These are the, the fundamental rules that you have to memorize. Okay. So again, just give me a second to recapture my cursor, which seems to come back when I oh, don't want to do that. Okay, so we have our initial condition. And now we need our time constant. To get our time constant, we need the equivalent impedance as seen by the inductor, right? So let me remove all the annotations. And now let's draw the picture of the inductor as an open circuit after time 0. So this is 5, this is 12, and this is 8. So how much impedance is seen by this inductor, right? To go from this terminal to this terminal, how much impedance do we encounter? Again, which resistors are in series and which are in parallel? $12 and 8 in series and in parallel with 5. Excellent. That's exactly right. You either take the 5 ohm path or you take the 8 plus 12 path, right? So it's 5 in parallel with 20, right? So again, no matter what, you're going to get to here and you're going to have to make a decision. You either take the 5 ohms and get back home, or you take the long way that takes you to the 8 and the 12, which also gets you back home, right? So 5 in parallel with 20 is equal to 4, which means that our time constant is equal to 2 over 4, which means that our final answer, I of t, is equal to 2 times e to the negative 2t. All right. Is there any questions on what we've done so far? All right. So answer, we're going to skip this one because the solution is in the lecture, like it's in the slides. We're going to go to problem number 4. All right, so same as before, we have a switch that goes from the closed position to the open position at time 0. And just to kind of reinforce the idea that this is a closed connection, I'm just going to draw it like that. And remember, this becomes an open circuit, a short circuit, sorry, right? So the inductor before time 0 is a short circuit. And we need to find how much current I is flowing through this short circuited inductor. So which resistor can we ignore in our analysis? The 3 ohm, excellent. The 3 ohm resistor can most certainly be ignored, right? So in our, okay. So basically we have a current source. The current comes out here. It can either go through the 4 ohm path this way, or it can take this path, the outside path, right? So how much, we need to know this current, which corresponds to the outside path. So how much current is flowing along the outside in this picture? Right, maybe if it help if I actually draw it out. I mean, I'll take the time to, so we have our current source. Our 4 ohm and our 2 ohm. And we are interested in this current. And this is 6. We have a chat answer, 4 amps. Yes, that is correct. The 2 ohm, so because of current division, right? Or wait, hold on a second. I thought it was 4 amps too, and then I'm looking at it, it's just 2 amps. Give me a second.
It's a different current.
Oh, this is I naught. This is I naught. So I naught is equal to, I naught is, so I is equal to 4 amps. I naught is equal to 2 amps, right? So this branch will draw 1/3 of the current, which is 2, and this branch draws 2/3 of the current, which is 4. So our initial condition, so this, I should have done, this is one of those cases where this is a question that I would have done on the board. And so I had just like the bare bones solution on the slide. Back here. So I naught is equal to 4 amps, right? And we need to figure out the value of tau, which is L over R E Q. So now let's draw this picture again after time 0. Okay, so now if you actually gonna clear everything. And so, and let's draw. So we have our inductor, which we're gonna just draw as an open circuit for computing the REQ. Right, and so we can ignore this is all gonna be gone because this switch is now in the open position. Right, and so this is 3, this is 4, and this is 2. And so how much resistance do we see from the vantage point of the inductor? So this is the REQ. So again, same question as always. Which two resistors are in series and which two resistors are in parallel? Or sorry, which resistors are in series, which are in parallel? Okay. 4 plus 2 in parallel with 3. Yeah, so again, so right, so the 4 and the 2 are in series. Yeah, so I think both of you are actually right. Both of you, correct, that 4 plus 2 are in series. So that's 6. That's in parallel with 3. So 6 in parallel with 3 gives us 2 amps. And so our time constant is 1/2 because our inductor has a value of 1 Henry. So 1 Henry divided by 2 ohms is a time constant of 1/2 second. And so our final answer for I of t is equal to 4 times e to the power of negative 2t. And I think we are also asked here for the, okay, so let me see what we are asked to solve for. Okay, so there's actually, so we are at, and this isn't, it didn't make it into the slide. So let me just, I'm gonna add it in here. So that we are asked to solve for I of t, VL of t. Yeah, VL of t. I think there may have been something else. Right, and I naught of t. Okay, so right now, we have only solved, we have a solution. Sorry, try to get my cursor back. So right now we have a solution for I of t, but we do not have an expression for VL of t or I naught of t, right? So we need to get, and we may have actually been asked to solve for VL of t, but let's just proceed. So the first thing to note is, if we know the current through the inductor, how do we get the voltage across the inductor? How do we go from inductor current to inductor voltage?
Voltage is the inductance times the derivative of the current.
That's right. And in this case, the inductance is equal to 1, right? So it's just di over dt because the L is equal to 1. And so what is the derivative of this, this expression? That's right. -8 times e to the minus 2t. And so now we have, with that, we can actually get, so notice that this inductor voltage is also the voltage that's sitting across the 3 ohm resistor. So this 3 ohm resistor is in parallel with the inductor, which means that it has a shared voltage, which means that I of 3, so I'm just going to annotate this here so that hopefully I won't lose my cursor for the 1 billionth time. So I'm going to call this I of 3 is equal to, and this is VL, right? Which is also applied to the 3 ohm resistor. So VL divided by 3 is equal to I of 3. So now the final part here is, at this node, remember, this is now an open circuit. What is the relationship between I of 3 I and I naught. I want to apply KCL at this node. Right, so they're all exiting the node, right? They're all exiting the node, which means that I naught, which is this current here, is just equal to I plus I3 with a minus sign in front of it, right? Because they're basically the KCL equation is the following: I naught plus I3 plus I is equal to 0, which means that I3, or I naught is equal to minus I plus I3, which is what is in the PowerPoint slide. All right, so try to get through this example here. Okay, so I naught is equal to minus I plus I3. We have an expression for I3, and we have an expression for I. So we add those together and we negate them, and you get a value of -4/3 e to the minus 2t. All right, so this is the final answer here. So before time 0, I is equal to 4 amps, and I naught is equal to 2 amps. After time 0, they each have an exponential decay. However, the I is starting from positive value and decaying down to 0, and I naught is starting from a negative value and decaying also to 0, I believe. Let me just double check that. As t goes to infinity, this goes to a very small number. So they all end up at 0. Okay. Here we have, let me just take a sip of my water. This is kind of a weird kind of segue in this lecture. So what I always say at this point of this lecture is that you don't like this section on singularity functions. It's a little bit superfluous in the sense that we definitely need you to guys understand what a step function is and what an impulse is. But besides that, you know, the amount of this material that we go on to subsequently use in lectures 8, 9, and 10 is pretty limited. So I'm just gonna also, because we're running up against time, I'm gonna kind of go through this quickly. So a singularity function is just, you can think of it as a switch. So in these RC and RL circuits, you have voltages or currents that turn on and off. So we need some mathematical instrument that can model that. And that's what these singularity functions do. So we're just going to introduce you to 3 different types. There's a unit step function, the unit impulse function, and the unit ramp function. Okay, so here they are in pictures, and the pictures are really the best way to understand these. So you've all seen the step function, starts out at 0, goes to 1 instantly, and then stays at 1. The impulse function is the derivative of this function, right? So if you take the derivative, differentiate this function, you get 0 everywhere except for at 0. So at 0, the derivative is undefined. So it's a function that starts out at 0, goes to infinity, and then goes back down to 0. And the ramp function is basically the step function multiplied by y is equal to x. So if you're positive, this is also called the hinge function sometimes. It's very popular in deep learning, actually. So this is it's a unit ramp, also known as a hinge. right. So why are we teaching you just the stuff in circuits? Well, the main thing is that sometimes the step happens at time 0, but sometimes it happens at another time t naught. And so if you evaluate the step function not at 0, but at not at time t, but rather time t minus t naught, the function shifts to the right. So think about the argument of the step function. If it evaluates to a number that is bigger than 0, the value of u is 1. If it evaluates to a number that is less than 0, it evaluates to 0. So this argument is only greater than 0 when t is bigger than t naught. In other words, if t naught is a positive number, this notation just means that the step function has been shifted by t naught units to the right. And so, if I have a question for you. This would be one of those chocolate award-winning questions. This is my u of t. And this is my u of t minus t0. So my question is to you, in going from this picture to this picture, have I, is this a shift? Sorry, is this a delay or is this a fast forward? In other words, have I moved the step to the past or to the future? So maybe I'm not phrased that clear. Let me just find the right words to pose this question. What I'm saying is this, in this picture, when I'm going from ut to ut of my to u of t minus t naught, have I advanced the step function in time or have I delayed it in time? All right, let's see what the audience says. Delay. That's right. Delay is right. It is a delay. And let me just get my cursor back and try to unpack that. So basically, this is the present time. Anything, if the step happened here, it would have happened before time 0. So it would have already happened. But since it's happening over here, it's happening at a later time, it's actually being delayed. So a shift, when t naught is positive, a negative lag means a delay, whereas a positive lag would have meant an advance in time. So anything that's out here has already happened. Everything that's out here has yet to happen. And this is the present time. All right, hopefully I didn't confuse too many of you there. So the voltage, all right, so if you have a function, let me just clear out this annotation. So if you have a function that is equal to 0 up until a certain time, and then it goes to another value, but not necessarily equal to 1, then it can be also expressed as a step function, right? So this function, v of t, right, means that there's a battery that gets turned on at a time of t naught. So if t naught is equal to 0, then this just means then this battery here, whose value is an actual function, is equivalent to the following picture. So these two pictures are equivalent. In picture 1, you have a battery whose voltage is now a function of time, where its value is v naught at time 0 and all times after 0, and it's equal to 0 before time 0. In the picture on the right, you have a battery with a constant voltage of v naught that is disconnected until time zero. And at time zero, it gets connected to the circuit. Right, so when this switch goes from this position to this position, all of a sudden, the battery gets turned on. So the step function just gives you another, like a mechanism for writing a battery that turns on at a certain time. So this means that the voltage is equal to V naught at all times greater than T naught. All right. Yeah, the unit impulse function. So I don't want to dwell too much. I'm actually going to, the only thing you need to know about an impulse is that it has an infinitesimally short width and an infinitely high area. So if you think about the way that this is usually taught is if you have, and again, I'm going to lose my cursor, but oh well. If you have a kind of a box car, right? And this is, the width is delta W and the height is H. So if you make H, so, and the area is equal to 1. So if delta W times H is equal to 1. Let's say that next you reduce the width by half by you, let me see, actually undo that. Next, you reduce the width by half by you double the height, all the same time keeping this relation. And you keep going, you keep making it narrower and narrower and taller. Eventually you will get to the impulse function, which is also called the Dirac delta function after the mathematician Paul Dirac. So the only thing you need to know about it, it has a finite area of 1 that is kind of a combination of a very narrow width, a very tall height. And that's all I'm going to say about it, because we really don't use it that much in this course. Okay, so that's the unit impulse function. It's just, yeah, it is what it is. Another way to think about it is that the impulse function is a derivative of the step function. All right. Okay, skip that. The ramp function we really don't use. The only thing that is useful to know is this property here, is that when you switch a function from being a function of t to being a function of t minus t naught, effectively you've just moved it, you've just delayed it in time by t naught units. So that we actually do use in a couple of the problems. Right, so this is the hinge function that's being delayed by t naught units. I'm going to skip through this because I don't think, and this slide, you can look at it at home. Basically, it just says that if you want to represent a box car, you can represent it as a kind of a combination of step functions. So if you have one step function with a positive area, and you add it to another step function of negative area, the sum of those two will be this boxcar shape. And you can do other tricks. You can basically synthesize different functions by combining ramps with step functions. But again, I don't want to dwell on that because I will point anything that you really need to know. I've pointed out the delaying of the step function is really the only component that you will use. All right. So now we move back into the stuff that is kind of critical for the course. So now we've been looking at RC and RL circuits without a battery connected to them or without a current source connected. Now we're going to look at what happens to an RC circuit or an RL circuit when there's a source that gets turned on and stays on forever. So before we had sources that are turned off at time zero. Now we're going to look at sources that turn on at time zero. And the result of that is what's called the step response. So why is it called a step response? And I think sometimes this isn't made clear. So if you have some system and you can input something into the system and you can measure the output, right? This is the output, and this is common in engineering. You're presented with a system and you need to figure out what that system is doing, right? This is the input. So step response is kind of a, you put in a step function and then you note what happens to the output. And maybe it's something like this, right? Maybe it's a function that, or maybe it's something like, like that, for example. And so the step response is the response of your system to a step function. And it is, it's very common in engineering to assess the step response of some system of interest. So in this case, the system is the circuit. And more precisely, it's the voltage across your capacitor, or it's the current through your inductor. And we will look at what happens to the capacitor voltage when it gets excited by a battery. And we will look at what happens to the current through an inductor when it gets excited by a current source. Okay. All right. Let me just try to rectify my problem. Okay, so again, as I just said, the step response of a circuit is the behavior when the input is a step function. So a source that was off and now is on. So note, and this isn't really spelled out in the lecture notes. So I'm saying it here. Before, we were looking at a battery that was on and gets turned off. That's source-free circuit. Now we're looking at a battery that was off and gets turned on. Okay, and so these two pictures are equivalent. So before time zero, the capacitor doesn't see anything. And after time zero, it sees a battery with a voltage of Vs that's connected to the capacitor in series with a resistor. All right. So Vs is a constant, for example, 5 volts or 10 volts or whatever. It's a DC battery. And we are going to be interested in what happens to this capacitor voltage as a function of time. Okay. The important thing is that at time zero, the capacitor voltage has to be continuous. In other words, V at time 0 minus epsilon has to equal to V at 0 plus epsilon. And those two values, that same values, we're going to call it V naught. So this V naught minus is the voltage just before the battery turns on, and V naught plus is just after the battery turns on. So this is our canonical picture of an RC step response. Okay, so we have a battery that is energizing an RC circuit. So let's apply either KCL or KVL. So it's the same kind of development as before, right? We have, so let's see, this is the current through the capacitor, right? This is the current down here. So it's a derivative of V multiplied by C. And then that has to equal to the current through the resistor. So the current through the resistor is, right, so let me actually annotate this. Right, so we have, this current here is V minus Vs ut over R. And this current here is, is CV prime. And those two currents have to equal to each other. Okay. And let me just, and that's how you get this equation here, which we can rearrange and kind of manipulate the same way as before. So now again, we have a first order differential equation. And the only difference is that whereas before we had no constant on the right-hand side, now we do have a constant of Vs over Rc. Before Vs was equal to 0. And so we kind of take the same path as before, where we turn the derivative of time into a derivative of voltage. So this is just algebraic manipulation, just rearranging terms. And now we're going to integrate both sides. Okay, so if you integrate this, it's the natural log of V minus Vs, evaluated at integration limits of V at time 0, which by definition is V naught, and V of t. And so you evaluate this and you get the following equation. You get natural log of Vt minus V of s minus natural log of V naught minus Vs is equal to a linear function of time. And again, you can rearrange the logs and exponentiate both sides. And what you get is the following. You base cross multiply here and you get that V of t is equal to a constant plus a decaying exponential. So the way to think about this equation, and this is an important one, is that this term here, V of s, is the steady state term. So this is the term that is always there at all time. This term here is a transient, right? So this term decays down to 0 once enough time has gone by. So the overall capacitor voltage is really a summation of a constant term, and that constant term has the same value as the battery, plus a kind of a transient term, which is starts out at V naught minus Vs and decays down to 0. So in other words, before time 0, this capacitor is an open circuit whose voltage is Vs. Sorry, let me just double check that. Whose voltage is V naught, sorry, not Vs. And V naught is just the initial value, whatever the initial value will. Sometimes it will be 0, but not always. Hold on, let me just look at this carefully. And after time 0, we have this kind of, it's a combination of a constant, which is given to us by the voltage of the battery, plus a decaying exponential. So before we had, if you said Vs is equal to 0, you'll get what we had before for the source-free circuit, that V is equal to V naught times e to the minus t over tau. So the difference here is that now we have a forced component. So Vs is sometimes called the forced or steady state component. It is the component of the solution that is always present. So here's kind of a picture that is common. So, you know, your voltage is starting out at some value V naught, and then when the battery turns on, your capacitor starts to charge up, and it will charge to a value of Vs, and then it will stay there. So it plateaus at Vs. So in physics class, when he talked about the capacitors charging, this is what that is in reference to, right? The battery turns on, at time 0, and all of a sudden there's a charge that gets built up across the capacitor. Okay, so the complete response of the RC circuit to a step voltage input is the equation on the previous page. So if V naught is equal to 0, then we have the following. So in other words, if the initial voltage on the if the capacitor was uncharged initially, then this V naught term is 0 and this V naught term is 0. And what we have is the following equation, that our capacitor is sitting there uncharged until the battery turns on. And when the battery turns on, the capacitor starts to accumulate charge up until Vs, right? So the capacitor will never have a voltage bigger than the battery. Right? You can't create energy out of nothing. But the battery will charge the capacitor. All right. So the current through the capacitor, as before, is given by the derivative of its voltage multiplied by C, right? And so, for example, whereas in the previous equation, in the previous situation where we had the capacitor starting out at 0 and charging up to Vs, the current is actually starting out at Vs over R and decaying down to 0, right? So when the capacitor is fully charged, it's no longer, there's no current flowing across the capacitor. There is current flowing through the capacitor during the charge phase. All right, so basically, if you take the derivative of this equation and multiply it by C, you get this. And so the current through the capacitor is equal to Vs over R times the decaying exponential, all multiplied by the step function. So basically, when you take a signal and multiply it by a step function, you're forcing it to be 0 up until time 0. So this is something we'll see commonly. Instead of writing a switch and saying when time is equal to 0, if we just multiply a function by the step function, you're forcing all of its values before time 0 to be equal to 0. Okay. And here's the recipe for solving RC/RL step responses, right? So our recipe is that our solution has two components. We have a forced component, a forced response, and a natural response. The forced response is just equal to the size of the step. And the natural response is given by the initial value minus the final value multiplied by our decaying exponential. Okay, so Vn is called the natural response, and it's also called the transient response because it goes away after enough time has gone by. Vf is known as the forced or steady state response because it comes on at time 0 and it stays on. So the sum of the forced response and the natural response is the total solution. Okay, so here's an important equation. Basically, V of t is equal to the V at infinity plus the difference between the initial and final conditions multiplied by our complex exponential with a time constant of tau. So what you will do to solve these circuits is analyze the circuit at 3 points in time. You'll analyze the circuit right before the step, right after the step, and at the end of the universe. Those are the 3 time points. And 2 of them are really close to each other, before and after the step. And we will do a bunch of examples, right? So you need 3 pieces. So this is really your recipe. Solve for the initial capacitor voltage, solve for the final capacitor voltage, and then solve for the time constant. And then you put them together. You're done. Just one note, if the switch happens not at time 0, so if that battery doesn't come on at 0, let's say it comes on at 2 seconds, everything stays the same, except that you just shift your response 2 units to the right. In other words, you delay your response. We'll do a couple of these as well. All right. Let's work through a couple of examples here. So notice, look at this capacitor, right? It's the switch is at position A, leading up to time 0. And then at time 0, the switch goes from position A to position B. When the switch is in position B, this capacitor all of a sudden will get energized by the 30-volt battery. Before the switch is turned on, it has been excited by the 24-volt battery. So our first step, as before, is to find the, first of all, we're asked to find V of t at time equals 1 second and 4 seconds. So we need this equation, basically. We need V of t. So we need three components. You need V naught, V of infinity, and the time constant. So let's start with V naught. So what is, looking at this picture when the switch is in position A, who can help me figure out what is the value of V at time equals 0 minus? So right before that switch flips. All right, so what if I'll try to draw a picture to make this easier. So we have our battery. We have our 3K resistor, our 5K resistor, and then we have our open circuited capacitor. Right, because this is at T. This is 3K, and this is 5K. And we are interested in this voltage. So in this picture, what is the value of V? Any ideas? Oh, come on. 15. Yeah. Christian, both of your answers are right. V is the same as the voltage across the 5K, and it is equal to 15. So it's 5/8 of 24, which I believe is 15. So it's just a voltage division problem. I think this one has, right? Just clear the examples, clear the annotation, right? So at the initial value of this voltage is just given by voltage division, right? So this 24 volts is dissipated across the 3K in series with the 5K. So 5/8 of 24 is 15. Okay, now what about the value of the capacitor at time equals to infinity? So when this switch goes to position B, and if you wait a very, very, very long time, what's going to be the value of this capacitor? Oh, I heard it. Not sure if that was just. Yeah, if you tried to answer, I didn't quite make it out. Oh, we got a chat. Oh, my cursor is gone again. This is unreal. Give me just 1 second. Right. Audience says 30. Excellent. 30 is right. Right. So the final volt. So this battery will charge up this capacitor. Right. So when the capacitor is charged up, it's an open circuit. And so the 30 volts will just appear across this capacitor. And so the last piece is the, go ahead. Christian, go ahead with your question.
So my question is like, how can it be 30? Like, I know it's 30 because it eventually reaches the source,
Yeah,
but how can it be 30? Because wouldn't that violate KVL?
that's a good question. Yeah, so no, the answer is it can be 30 and it doesn't violate KVL. And so here, let me do something to, just give me a second here. I think this is just kind of an artifact of the way this is like, I feel like the way it's taught in high school is wrong, and the way that it's taught here isn't ideal either, but basically. So if you have a capacitor, you have a resistor, you have a battery. Oh, forgot the minus pole. Anyways, this is a battery. All right. And so let's say this is 30 volts. And this is V of C. So the reason it doesn't violate, so at the beginning, let me see if I don't know, hopefully I'll be able to explain. So right at time 0 plus, you have, or let me actually, let's actually look at the case. Let's actually look at the time equals infinity case. So what happens at time equals to infinity? Basically, at time equals to infinity, this is an open circuit because the capacitor has been sitting there for a long time without any change. It hasn't seen anything changing. So the capacitor responds to a change in the terminal voltage. So it essentially is an open circuit. So there is no more current that is flowing across this circuit. And so this picture essentially gets distilled down into the following. Because there's no more current flowing across, because the capacitor has gone from, converts to an open circuit, right? So there's the reason that KVL isn't violated is because this resistor is dead. So the entire voltage of the battery has been transferred to the open circuit capacitor, but no current flows. So when the current is flowing, then the capacitor voltage has not yet reached 30. So the picture is, so if you look at the capacitor voltage, it's something like this. And if you look at the capacitor current, it's something like this. Okay, so the capacitor voltage charges up while its current decays down. All right. Let's see, where were we? You're welcome. We were here. All right, so we got the initial condition, we got the final condition, and basically the time constant is easy to get because this capacitor only sees the 4 kilo ohm resistor. So 4 kilo ohms times half a millifarad is equal to 2 seconds. So the final solution is 30. Aisha, you're unmuted. The final solution is 30 plus 15 minus 30 multiplied by e to the minus t over 2. Right? This is the time constant. This is the initial condition, excuse me, and this is the final condition. Give me just 1 second. Okay. All right. Let's. Oh, I didn't animate this. I didn't animate this one. But let me see. Maybe I did. No, I guess not. All right. So let me walk through it step by step. Okay. So first of all, what are we asked for? We're asked to find V of t for all times greater than 0. And maybe what I'll do is just, it's distracting for me to have the answer there. Okay. So let's draw this. So at time 0, the switch goes from the closed position, sorry, from the open position to the closed position. So before time 0, the capacitor only senses the 10 volts. So who can tell me the initial value of the voltage here? So you can ignore all of this. All we have is this circuit. Okay, well, guess I will just answer my own question. So the initial value of the capacitor is just equal to 10 volts because of exactly what I just went through in that previous question, right? So in steady state, this is an open circuit. And this capacitor is at steady state leading up to time 0. So right before time 0, this capacitor has been sitting here for a very long time. And it senses this battery, and it has effectively been relegated to an open circuit. And all it senses is a 10-volt battery. So the initial value of the capacitor voltage is 10 volts because there's no current flowing around this loop. All right, let me see if I can. Maybe what I'll do for this, I'll actually take myself out. Yeah. Okay. I think the annotation will work better like this. Okay, so at time 0, is equal to 10 volts, right? So that's our initial condition. And now we have to analyze the circuit at time equals to infinity, right? So at time equals to infinity, this circuit looks, so again, at time equals to infinity, the capacitor is an open circuit. But now it's connected to the other side of the circuit. Okay. So what is the value of the V in this picture? Right, notice this is an open circuit, so there's no current flowing. Which means that V of t is equal to what? Minus 50. Right. So this is the voltage at time equals to infinity goes to minus 50 volts. Right, because its polarity, the polarity of this battery is opposite to this capacitor. And so this resistor, the 6 ohm resistor here is dead. And the reason it's dead is because the capacitor has been open circuited. And so current is not allowed to flow. There's not a closed path for the current to flow. But KVL still has to hold, right? So if we were to apply KVL, it would be minus V minus 50 is equal to 0. In other words, V is equal to minus 50. And the last piece is that time constant tau is equal to RTH times C. And the RTH here is equal to 6 ohms because that is the only resistor that this capacitor sees after time 0. So 6 times 1/3 is equal to 2 seconds. And so the final answer for V of t is equal to, as before, I'll just write the minus 50 plus 60 exponential what did I? Oh, I told him, I'm so sorry. I made a mistake in this. That's what I get for let's see, that's what the question was about. So when I was going through this, I felt like, I don't quite remember these numbers, and sure enough. So let me roll back. I'll have to edit the YouTube video. I can't possibly show me making a mistake online. So let's go back actually and redraw, because I actually forgot about something. I forgot about half the circuit. So let's look at, again, draw the picture. So this is correct, but V of infinity is not correct. So I'm going to redraw this circuit. Maybe that's why everyone was silent, or maybe it's because people have just given up. Let me try to, okay. This is a 10 volt. And we still have the 2 ohms. Actually, now that I remember it, I really like this question. Okay, so here's our picture. This is 2 ohms, and this is 6. and this is 50. So the key to this, I believe, is to figure out how much current is flowing along this path here. How much current is flowing clockwise. Notice that everything is in series, right? So if you have two batteries in series, what can you do to their values? Add them, right? That's how, like, when you put I don't know if you guys watch TV, but if you have a remote control at home, for example, and your remote control takes 4 AAA batteries, they're always added in series. Oops. Oh, come on. They're always added in series so that their voltages add. So you get basically this 50 and this 10 get added into a 60, right? And this 2 and the 6 get added into an 8. So how much current is flowing along this loop? So it's 60 volts and 8 ohms. Yeah, 60 over 8. So that's like 7.5, I believe, so 7.5 amps. Right. So if we have 7.5 amps going this way, right? And this is ground. So this point here is sitting at 10 volts by definition. What is the voltage over here? Right, this is V. So how much is the voltage drop from here to here? Right, so the resistance is 2. And the current we just said was 7.5 amps. So the drop from here to here is 15 volts. So in other words, this point here has to equal to -5. Okay, I will just guess I will, let's see. I'll just go here because here I had the solution, right? So see if I can. Okay, so the initial value was 10 volts. That's clear. Then the value at time goes to infinity, we just solved to be -5 volts, right? And the time constant is just 6 ohms times 1/3 of a farad, which is oh, actually, I that's a mistake too. Okay, so we have the 2 ohms here. We short circuit the battery. I just completely forgot about the left side of the circuit in this problem. And then we have, right. So whenever we find the Thevenin resistance, we have to disconnect the independent sources. So the 10-volt battery and the 50-volt battery have both been disconnected. And so our Thevenin resistance is just equal to 2 in parallel with 6, which is equal to 12 divided by 8, which is 1/2 ohms, which means our tau is equal to R times C, which is 3/2 times 1/3, which is 1/2 of a second. And that's what you see here. And so finally, we arrive at our final solution, which is -5 plus, let me just kind of unpack this. So our final solution, V of t, is equal to our final plus the difference between our initial and our final times and when you plug in the values that we just solved for, right? And so our initial was 10 and our final was -5. So the difference between them is 15. And this is how we construct our final answer. So I apologize here for convoluting the solution. I'll try to do better on this next one. Let me just quickly pause sharing for just 1 second and just look at which ones I want to cover before the end of the class and which ones I want to skip. Okay, so what I'm going to do is I will skip the next example and we will do okay. Resume share. Okay. So let's try to put this on slideshow. Okay. So we have the following circuit. There are two sources in it. We have a battery whose value is 20 times u to the minus t volts. And we have a current source on the right with a fixed value of 3 amps. So is this battery on or off before time 0? My first question to you. Before time 0, is this battery on or off?
On.
It's on, right? Because before, when t is negative, minus t is positive. And when the argument of the step function is positive, it evaluates to a positive number. Okay, so now, as always, let's draw this circuit at different time points. So let's draw this circuit. I'll try to be neater. Let's try to circuit at t equals or t right before time 0. I don't know, they'll let me do a superscript. So I'm just going to write it like that. So okay, so at time equals to 0 minus epsilon, this battery is on. It's connected to our 5 ohm resistor. And our capacitor has been sitting there for a very long time without any change to its terminals. This switch has yet to close. So the entire circuit just looks like this. So what is our initial value for I of 0 and t of 0? I could have really used a chalkboard for this problem, but I'll do my best here. So what is the value in this picture of I, which is here? And V, which is here.
would it be 4 amps and 20 volts?
It is 20 volts, but it's not 4 amps. Because there's no closed path for the circuit to flow. All right, so it is 20 volts. And but it's 0 amps because whenever you have an open circuit like this, then there's nowhere for the current to flow. Right, but so in other words, this capacitor is fully charged. And when the capacitor is fully charged, it is no longer, it's no longer carrying a current. All right. So
Sorry.
now let's draw. Actually, let me just do something. I like this pause share feature. I'm just gonna to avoid what happened last time. I'm just gonna make sure that I don't screw up on any of these. That I don't solve I don't show you the wrong solution again. Right. So okay. So now let's look at the other end, the other extreme, which is time equals to infinity, right? So at time equals to infinity, this battery is short-circuited. So we're just gonna draw it as a short. Our capacitor is once again an open circuit. Right, the switch is closed. And our current source is now in play. Right, so we have 3 amps flowing here. We have 10 here. We have 5 here. So now my question, and then the quantities that we're interested in is I and V. Okay, so how much of that 3 amps goes to the 10 ohm resistor and how much goes through the 5 ohm resistor? So I think solving for I is easier here.
2 amps goes to the 5 and 1 goes to the 10.
That's right. Excellent. And so what does that mean for the value of I? If 2 amp, like the current, so 1 amp goes down here and 2 amps goes here. So what is the value of I in this picture?
-2.
Excellent. So I is equal to -2 amps. And what is the relationship between, so if I draw, yeah. Right. So the voltage drop from here to here is equal to 5 times -2. And this is ground, right? So this is 0 volts, and there's a drop of -10. So 0 minus -10 means that this is sitting at 10 volts. And so V is equal to 10 volts. Notice that V starts out at 20 and goes to 10, whereas I starts out at 0 and goes to -2. All right, so now we've done 2/3 of the work. The remaining third is to evaluate the the time constant, the Thevenin resistance as viewed by the capacitor. So what I'm going to do is I'm going to disconnect the sources. So we're going to look after time 0. So after time 0, the battery on the left doesn't even exist. And we have this picture. So we have resistance of 5 and a resistance of 10. So here the RTH is, I think it's just 50 over 15. So right, a 5 times 10 is 50. These two are in parallel. So 50 divided by 15, which is, let's see, what does that
3 and a
reduce
third.
to? Say it again.
3 and a third.
10 over 3, I think, yeah. 10 thirds. So our tau, which is equal to RTH times C, is equal to 10 thirds times 1/5, which is 2 over 3, I believe, seconds. So now we can write at least our solution for V, right? So V of t is equal to V infinity plus 0 minus V infinity times exponential. So and I will then plug in the numbers. So V of infinity was 10 plus V naught was 20. So 20 minus 10 times exponential minus t. So minus, I was going to call this minus 3 times t over 2. And that is our solution for V of t. So the only thing that is left now is to solve for I of t. So the time constant of I is going to be the same as the time constant of V. And so I think we can just take this. Oops. Oh, come on. Are you really that? This thing does not like cut and paste. All right, so let me just. So the final value was 10. The initial was 20 minus the final of 10 because 10 times exponential 3t over 2. And then I of t will have a similar value. It will have a similar form. Basically, the final value for I was -2 plus the initial value of 0 minus the final value of -2. So minus -2. I'm just going to write this as +2 times exponential -3t over 2. And let's hope that that is the correct answer. Let me just see here. I will go back to the slide that has the solution. And it does look to be the correct answer. So I guess I'll just kind of, I'll review the solution. So the first thing we did is we drew the circuit right before time 0. And we saw that the voltage on the capacitor was just simply equal to 20 volts of the battery. And there was no current flowing through here because there wasn't a complete path for the current to flow. Then we went to time equals to infinity. When time is equal to infinity, this switch is closed. This is a short circuit. And we saw that the voltage on the capacitor was equal to 10 volts and the current through the resistor was minus 2 amps. And then we found that the time constant was equal to 2/3 of a second. And then we plugged everything into a standard solution. And so, for example, the voltage starts out at 20 and then decays down to a value of 10 times 1 plus e to the minus 1 and 5t. So for example, when t is equal to 0, this term here evaluates to 1. So 10 times 1 plus 1, that equals to 20. So notice that there is continuity here, right? So at time equals to 0, the voltage doesn't undergo an abrupt change, right? It goes from 20 down to 20, and then it starts, I'm sorry. So it goes to 20, stays at 20 during the transition from when this current turns off, and the switch closes. And as time goes on, that voltage slowly or decays down exponentially to a final value of 10 volts. The current starts out at 0, and eventually it goes to a value of -2, right? So it's starting from a point of 0, from initial value of 0, and decaying down to -2 amps. All right, I'm gonna wrap it up here. So we're 3/4 of the way through lecture 7. So as I said at the beginning of lecture 7 content, lecture 7 and 8 are the most demanding, represent the most demanding content in this course. The essential kind of, or the critical concepts kind of carry over. Namely, you have an initial condition, you have a final condition, and you have a time constant. And then you have a recipe for how those 3 components get synthesized into the final solution. So I'm gonna work hard over the next, I guess, 2 weeks to try to present the material in a way that is most accessible to you. I know even when I was teaching this in person, this was always a very, very hard lecture to present, and I recognize that the material is not as accessible to you guys. I encourage you though to kind of go through this lecture slides on your own time. It really helps to have repeated exposure. So like if you just kind of start at the beginning of lecture 7 and work your way up to where we are now, I think it will greatly benefit you on Wednesday when I will cover the step response of an RL circuit. So the good news is that the step response of RL is almost identical to the step response of RC. The only difference is that instead of solving for the capacitor voltage, we're going to be solving for the inductor current. Everything else stays the same. Remember, the homework one is due 1 week from today. The labs start 1 week from today during class. Thanks to those of you that actually stuck with me throughout the whole lecture. I know it wasn't easy to get through. I wish you all a good 48 hours, and I will see you all on Wednesday.